Hello, Betsy Dobbs McAuliffe again, and we're going to be continuing with Chapter 12, Transport Across Cell Membranes. In the last video, we covered action potentials, which are changes in membrane potential. They are also the electrical signals that travel down neurons. We can see a graph of an action potential in this image here, where we would have resting potential. We would have a stimulus that brought the membrane potential to the point of threshold where voltage-gated sodium channels would open, sodium would rush into the cell, depolarize the cell, and the sodium channels would inactivate, potassium channels would open. Potassium will flow out of the cells, taking along with it its positive charge, making the membrane potential, the interior of the cell, more and more negative with respect to the exterior of the cell. And this, of course, would be one action potential. However, an action potential does not happen at just one point along a neuron. Action potentials need to travel with successive sodium and potassium channels opening and closing, much like dominoes falling. This process is called propagation. So if we're thinking about an action potential, we're going to think of that as happening along the axon. An action potential is not going to occur at just one point along the axon. It's going to travel down from a point near the cell body toward the end of the nerve terminal. We can visualize the movement of an action potential down an axon by measuring the membrane potential at various points along the axon. Here we're focusing in on a particular region of the axon. I'm kind of blowing up that image, zooming in. And we can see in the image that we're putting in electrodes at particular points along the axon. And we're going to measure changes in membrane potential at each particular point. If we follow the graph here, we can see that the membrane potential first depolarizes at position V1. So the membrane potential here is depolarizing what they're calling about the zero time point. So we have a depolarization happening at this point. And we can see that the membrane potential, as read by this particular electrode, is going to decrease over time, go back to resting potential by 1 millisecond. The membrane potential at V2 is 0 at time 0, but by the time we hit 1 millisecond, the membrane potential at V2 is completely depolarized. And then it goes through repolarization at that position in the membrane. By the time we hit 2 milliseconds, the electrode at point V3 is recording a depolarization and action potential occurring. So hopefully this allows you to see that the membrane potential is not just depolarizing in one point along this very long axon. It has to travel along the axon. Again, this graph is showing a measurement of the difference in charge across the membrane. But what's actually causing those differences in charge is the opening and closing of sodium and potassium channels. I find this is best seen through a video that's provided by the textbook. And I'm going to give you a little background so that the video makes sense. Again, we are looking at the axon of a neuron. This is an axon at time point 0, and this is an axon at time point 1 millisecond later. Okay, so it's showing the same thing over time. Right? And so we have the phospholipid bilayer on each side defining the axon, and they're showing here just the sodium channels. And we have the depolarization of the membrane is traveling. So the blue is the action potential. We have depolarization happening right here for this particular sodium channel. And we can see that sodium is flowing down its concentration gradient from high to low. The sodium channels behind it are already inactivated, and the sodium channels in front of it, closer to the end of the axon, are in a closed position. As sodium travels into the axon of the neuron through this particular ion channel, the sodium is going to raise the membrane potential. It's going to make it more and more positive here until we get to a point where we reach threshold in this region of the membrane, at which point we're going to open the next ion channels along the way, and we're going to inactivate the ones behind. So the action potential propagates or moves down the axon as sodium enters. While sodium will enter the cell and can diffuse towards the cell body and towards the end of the axon, when the sodium moves towards this region, it's still depolarized and the ion channel is open, but it is inactive. So the shape is open in terms of the pore, but the cork has been placed in. So the action potential will not travel backwards. It only travels forward because of the conformation of the sodium channel in the direction towards the axon terminal.
The fundamental task of a nerve cell is to receive, conduct, and transmit signals. Neurons propagate signals in the form of action potentials, which can travel great distances along an axon without weakening. To transmit an action potential over such a distance without weakening requires that the signal is continuously reamplified along the way. The central molecular players in this process are the voltage-gated sodium channels, which undergo a cycle of finely choreographed conformational changes. When an action potential passes, sodium channels open in response to membrane depolarization. Sodium ions rush into the axon, further depolarizing its membrane. Within a fraction of a thousandth of a second, however, the sodium channels switch to a new inactivated state, in which they are closed, but now also refractory to reopening. In this way, the membrane potential can recover quickly after an action potential has passed. The sodium channels then reconvert to the closed state, ready to be opened again when the next action potential is encountered. Let's examine the changing state of the sodium channel during an action potential. When no stimulus is present, the sodium channels remain closed, and the electrical potential measured across the membrane remains constant. However, if a depolarizing stimulus is applied by a brief pulse of electric current, the membrane will start to depolarize, away from the resting potential of about -80 millivolts. Some of the sodium channels will open, permitting sodium ions to enter the axon along their concentration gradient. If the depolarization is sufficient, even more sodium channels open, and the membrane potential rapidly approaches the equilibrium potential for sodium, about +40 millivolts. At this point, the sodium channels close, adopting the inactive conformation, where the channel is unable to open again even though the membrane potential is still depolarized. The sodium channels will remain in this inactivated state until a few milliseconds after the membrane potential returns to its initial negative value. The action potential is propagated along the length of the axon in only one direction. By examining the membrane potential and state of the sodium channels along the length of the axon, we can see why this is so. As a depolarizing stimulus reaches our section of the membrane, sodium channels open and current flows into the axon. This in turn depolarizes adjacent sections of the membrane, causing adjacent sodium channels to open, and the action potential is thus propagated along the axon. Sodium channel inactivation prevents the depolarization from spreading backward along the axon.
We have just seen how an action potential can travel as an electrical signal down a neuron. However, we have not discussed what initially triggers the action potential. To understand excitation of neurons, we will look at the synapse. This is the point where neurons meet. So the axon of one neuron, which would be called the presynaptic neuron, meets up with the dendrites of another neuron called the postsynaptic neuron. So electrical signals travel down the axon of the presynaptic neuron and are converted into a chemical signal. This happens when synaptic vesicles, which contain cell signals called neurotransmitters, fuse and are released into the space between the two neurons, received by the postsynaptic neuron, which can then convert the signal back into electrical signal. So we have an electrical signal traveling down the presynaptic neuron, temporarily converted into a chemical signal, a neurotransmitter. The neurotransmitter is received by the postsynaptic neuron, and then a new action potential can be triggered in the postsynaptic neuron, converting the signal back to an electrical signal. So now we're looking closely at a cross-section of a synapse. We can see that the neurons are very close to one another, but not attached. Here we have two presynaptic neurons in yellow and one postsynaptic neuron in blue. The presynaptic neurons have these circles here which represent synaptic vesicles containing neurotransmitters. You can see they are closely aligned to the point in the synapse where the two membranes are very close, the membrane of the postsynaptic neuron and the presynaptic neuron. In this electron micrograph, we can see a synapse or synapses in real cells. Again, the synaptic cleft is circled in red, and we can see synaptic vesicles full of neurotransmitter. You may also note that there are synaptic vesicles right against the presynaptic membrane where they are ready to fuse. So again, the synapse is the point where an electrical signal or action potential is converted to a chemical signal or neurotransmitter. Then the chemical signal or neurotransmitter activates an electrical signal in the postsynaptic neuron. Let's take a look at these steps. So here we have a neuron prior to firing and after an action potential has traveled down the neuron. You can see that as the action potential is arriving through propagation, right, sodium and potassium channels open. At the end of the axon, there's calcium channels. These are also voltage gated, meaning depolarization is going to trigger their opening. Calcium is at a high concentration outside of the cell, so when the channel opens, calcium will enter the cell, moving from high to low concentration. In the absence of calcium, the synaptic vesicle, those circles that we saw in the previous images, right, synaptic vesicle is just it's very similar to an organelle, but it's just kind of a sphere of phospholipids. And this sphere of phospholipids, this vesicle, contains neurotransmitter. It's right next to the membrane of the presynaptic neuron. However, once calcium is released, this causes a fusion or a mixing of the phospholipids from the vesicle with the cell membrane. This releases neurotransmitter into the space between the two neurons, or synapse. So we can now see the neurotransmitter in the synaptic cleft, and then we have a receptor for the neurotransmitter in blue. When neurotransmitter binds to the receptor in the postsynaptic neuron, the receptor undergoes a conformational change. In this case, the receptor is also an ion channel, a ligand-gated ion channel. The ligand in this case is the neurotransmitter, and neurotransmitter binding to the receptor causes the channel to open. This will cause a change in the membrane potential of the postsynaptic neuron.
Neurons transmit chemical signals across synapses, like the one shown in this electron micrograph. We can identify the dendrite of the receiving or postsynaptic cell, as well as two presynaptic nerve terminals loaded with synaptic vesicles. Note the narrow cleft separating the pre- and postsynaptic cells. The synapse converts the electrical signal of the action potential in the presynaptic cell into a chemical signal. When an action potential reaches a nerve terminal, it opens voltage-gated calcium channels in the plasma membrane, allowing calcium ions to flow into the terminal. The increased calcium in the nerve terminal stimulates synaptic vesicles to fuse with the plasma membrane, releasing their neurotransmitter cargo into the synaptic cleft. The released neurotransmitters diffuse across the synaptic cleft, where they bind to and open the transmitter-gated ion channels in the plasma membrane of the postsynaptic cell. The resulting ion flows depolarize the plasma membrane of the postsynaptic cell, thereby converting the neurotransmitter's chemical signal back into an electrical one that can be propagated as a new action potential. The neurotransmitter is quickly removed from the synaptic cleft, either by enzymes that destroy it, or by reuptake into the nerve terminals or neighboring cells.